Hello everyone and welcome to this first year presentation on proof. So we're going to look at various different types of proof that you have to learn in year one. But before we can do that, I need to ask you on your whiteboards or on a bit of paper, please, can you write down for me the general form for any even number? Do that now for me, please, on your whiteboards. Okay, good. And if you've done that correctly, you should have the expression 2n. N can be any letter, that's just an arbitrary letter that we've chosen, but N does tend to be the one that is chosen most often. And as well as that, please, I'd like you to write down the general form for any odd number. Do that now, please. Now, the reason why we're asking you to do these is because these general forms are often used in the proofs that we do. So it's important that we understand what they are. So the odd number generalization is 2n plus 1. Again, n is an arbitrary number. The most common mistake that we see here is that students put n plus 1 rather than 2n plus 1. But the only way we can guarantee that we've got an odd number is if we take any even number and add 1 to it. There are other variations. You can have 2n minus 1, for example. So 2n plus 1 and 2n minus 1 tend to be the most commonly used expressions. Okay, so moving on, what I'd like you to do now on your whiteboards or on a bit of paper is write down for me 3 consecutive numbers. That's not algebraic, that's just 3 actual consecutive numbers, please. Any 3, write them down now for me, please. Okay, good. So the 3 consecutive numbers that I've written down are 6, 7, and 8. They are 3 integer values that come after each other on the number line. So we could have had 20, 21, 22. We could have had minus 20, minus 19, minus 18. I'd like you to now please write down 3 consecutive numbers generally. So this is algebraic, please. 3 algebraic terms that represent 3 consecutive numbers, please. There are many different answers we could have for this question, but I'm going to show you the most straightforward version, but I'll just give you a few more seconds to write your answer down. Okay, good. So the 3 consecutive numbers that I have chosen are where n is my first number, n plus 1 is my second, and n plus 2 is my third. And I'm concentrating on the most straightforward of these examples because the most straightforward is going to be the one that is easiest to use when it comes to the proof work in just a moment. So to finish off, please, can we write down perhaps the most straightforward general form for 3 consecutive even numbers, please? Write that down now for me. You'll notice that I'm still using N as my letter. That's mainly because it's the most commonly used letters when we are dealing with this topic. So my most straightforward even number is 2n, and then to get the next even number after that, I would have to add 2 on, and then for the third consecutive number, I would have to add 4 on to my 2n. So they're my 3 consecutive even numbers. Next thing I'd like you to do, please, is to write down the general form for any rational number. So clearly there has to be an understanding here of what a rational number is, but have a go. Write down the general form for any rational number. And the rational number that I have written down is a over b, where a and b are both integers. And the reason for doing that is because a rational number is defined as any number that can be written as a fraction. So a over b, b could be 1, for example, so whole numbers can still be represented as fractions. The only numbers that are not included in this list are the irrational numbers, which we will look at a future time. So rational numbers can be written as a fraction, so therefore I've written them as a over b, where a and b are both integers. We now have a symbol, which is often used in proof. You may or may not have seen this symbol before, but it represents the imply sign. So we'll have a look at an example. So this notation here would mean that if P is true, then Q is also true, and exclusively true at that, but we'll come on to some examples to explain that in just a moment. So here is an example. So if x is equal to 4, then it implies that 2x is equal to 8. There is no other value that 2x could take if x is equal to 4. So if x is equal to 4, it implies that 2x is equal to 8. And similarly, if 2x is equal to 8, it implies that x is equal to 4. There is no other value that x could take, and therefore this particular example works both ways. And as a result of it working both ways, we can write this symbol to imply that it works both ways. We've got the double-headed implication arrow being used for this particular example. Here's another example. What symbol would we use in this particular example? So we've got x equals 4, we've got x squared equals 16. What symbol would we use between these two equations? Well, it's certainly true that if x is equal to 4, it implies that x squared is equal to 16. However, working the other way, x squared equals 16 does not exclusively imply that x is equal to 4, because if x squared is equal to 16, then x could also be minus 4 as well. Therefore, the symbol that we would use works only from left to right in this particular example, not from right to left as well. So your turn now. What I've got here are 1, 2, 3, 4, 8, 8 expressions, 8 questions. And what I would like you to do, please, is to choose the right symbol for each of these particular questions. So you can pause the video now, please. Have a go at deciding on what symbol should be put in between the statements. And then when you're ready for the answers, press play and I will go through those answers. So number one, the symbol that we would use in this case is the one from right to left. If we have a rectangle in front of us, it doesn't necessarily imply that that is a square. We can draw lots of rectangles that aren't squares. However, if we were to draw a square, it is a special type of rectangle where all the sides are the same length. So therefore, we are implying from right to left. In number two, our symbol is going from left to right. If we have an odd number in front of us, then it has to be a whole number. But if we have a whole number in front of us, it doesn't necessarily mean that it's odd. So just left to right in this example. Number three, we're going from right to left. If we can run 2 kilometers, it doesn't necessarily mean we can run 5, but if we can run 5 kilometers, then it does imply that we can run 2. So right to left in this particular example. We move on to the triangle question, and in this case, the symbol works in both directions. If we have a triangle with 2 equal sides, it implies that that triangle must have 2 equal angles as well. And if we have a triangle where there are 2 equal angles, then the implication is that it must have 2 equal sides. So both ways work in that particular case. Number 5, only from left to right. If we have a prime number, then it has to be an integer. But if we have an integer value, then it doesn't necessarily have to be prime. Number 6 works in both directions. If A and B, if neither A nor B is true, then it means that A and B are both false. And if A is false and B is false, it implies that neither A nor B is true. So both directions in this example. Next one, if 2 circles have the same area, then basically they are the same circle. We can't draw 2 different circles with the same area. So if 2 circles have the same area, then it implies that they must have the same radii. And if we have 2 circles with the same radius, then it implies that we must have 2 circles with the same area. They have to be identical circles. And then finally, in the bottom question, a new symbol for us, which is where it doesn't work in either direction. And you can see that we have a line through the symbol, because if we have a regular shape, it doesn't necessarily have to be a hexagon. And if we have a hexagon, it doesn't necessarily have to be regular. So in this case, it works in neither direction. And so we use this symbol that you're seeing here. But we don't use that symbol very often, but it's there in case we need it. Okay, good. So now that we've looked at the general expressions and the notation attached to proof, we now need to actually look at some examples. Now, in first year mathematics, we're going to look at two examples of proof. We're going to look at proof by deduction, which is the one that you've probably seen most at GCSE level as well. We're also going to look at proof by exhaustion in this presentation. And then the final example we're going to look at is where we have a disproof by counterexample, but we'll come on to that a bit later on. So the first method of proof that we're going to look at is called proof by deduction, showing something that it is true by deduction. And this is commonly used at GCSE level as well as A level. So I will show you an example, and it should be quite familiar to you. So you can write all of this down in your notebooks, please. So we have to prove that the product of any two odd numbers is also an odd number. So there's some words in here that we have to obviously understand. So first of all, product. I think that really is the only word that we really need to discuss. The product of any two numbers is when we take those two numbers and we multiply them together. So the product is the result of multiplication. So we've got to decide on a general form for my two odd numbers. And the most common mistake that students make with this question is that they use the same letter for both. So they might use n for the first one, so 2n plus 1 would be their first odd number, and then they use 2n plus 3 as their second odd number. Well, we're being a bit restrictive there because what we've decided upon if doing that is that we are choosing two odd numbers that are next to each other, two consecutive odd numbers, and that's not what this question is asking. So when we're writing down our two odd numbers, we're using two different letters to represent just two random arbitrary odd numbers. So 2n plus 1 is my first odd number, and 2m plus 1 is my second. The choice of n and m was completely mine. If you want to choose two different letters, then that's perfectly okay. And what I'm going to do is I'm going to find the product of these two odd numbers by multiplying them together. So I'm going to expand these brackets and I achieve this as a result. So I've now found the product of those two odd numbers, and now it's my job to prove that this is also an odd number. And you can do it a few ways. I mean, your explanation skills are now where you're going to get any final marks for this question. So you could describe the fact that 4nm has to be an even number because it's a multiple of 4. You could then describe that 2n has to be an even number because it's a multiple of 2. You could then say 2m has to be an even number because it's a multiple of 2. Therefore, when you add those three even numbers together, you get another even number, and therefore by adding 1, you end up with an odd number. So as long as your explanation skills are good, and you explain to the examiner very clearly but yet very concisely what you mean, then you will get those marks. The alternative, and perhaps an easier way, is to talk about this expression that we've ended up with can be written like this. And this is the general form, of course, of an odd number. Two lots of something plus 1. So you could show that it represents an odd number by taking that multiple of 2 out and writing it as a general odd number. And that would be enough for the proof, and we would say that it's been proved. So there are various ways, and as you do more of these questions, you will see the different methods and the different techniques, and you will be able to make good choices as to what method of proof you should be using, because each exam question is different, and sometimes they don't actually tell you what method to use, so that would be your choice. But practice makes perfect with questions like this. So here's your second example for your notebooks. This time we're going to look at a method of proof called proof by exhaustion, which does exactly what it says. We're going to look at all possible examples for a particular situation, and by proving that it's true for all those situations, we are therefore proving that it's true overall. So an example of proof by exhaustion, and remember, you might be told the method to use, you might have to decide for yourself, but the question that we're going to answer is prove that any odd number squared always ends with a 1, a 5 or a 9. Now, I'll take you back to GCSE and talk about the most common mistake that we would see on a GCSE paper, is that students try it for maybe a half a dozen to a dozen arbitrary odd numbers, and they prove that all of those values, when you square them, end in a 1, 5 or 9, and they think therefore that they have proved it for all, whereas of course they've only proven it for the ones that they've decided to use within the question. So how can we prove that it's going to work for all values by looking at all values if we're not going to list all the different odd numbers that are possible? Because clearly that is an impossible task. So we're going to use a little trick, and we're going to use the fact that we don't have to try every odd number. We only have to try the odd numbers up to 10. So 1, 3, 5, 7, 9. And we would explain to the examiner that the reason why we only have to look at those values is that the unit value of the product of two integers is only determined by the unit columns of the integers themselves. So what I mean by that is that when I am multiplying two numbers together, I only have to look at the two values at the end of each number to decide what my final number will end in, what the product will end in. So if I'm multiplying two numbers, one of them ends in a 3, one of them ends in a 4, then straight away I know that my product will end in a 2. Because 2952 has the same unit value as 3 times 4. So 3 4s are 12, the unit value of 12 is 2. So as long as we explain that to the examiner, then all we then have to do is look at the numbers 1, 3, 5, 7 and 9. Because then as soon as I move on to look at 11, it's going to behave in the same way as the number 1 did. When I look at 13, it's going to behave in the same way as 3 did. If I look at 47 squared, that's going to behave in the same way as 7 did. Okay, so I only have to look at 5 numbers to prove that it works for all odd numbers. So I do have to look at those 5. So I'm going to list them, and I'm going to say that when n is 1, when we square 1, we get 1. When n is 3, n squared is of course 9. When n is 5, n squared ends up being 25. Similarly for 7, we get 49. And finally, when n is 9, n squared is 81. And you can see that all 5 of those square numbers end in either 1, 5 or 9. So if I was to choose any other odd number, then it would end in either 1, 3, 5, 7 and 9, and therefore when I square them, it will behave in the same way as these 5 numbers are doing here. So all of these 5 cases end with a 1, 5 or 9, which therefore means that it's true for all odd numbers. So by stating to the examiner a little mathematical fact at the beginning of the question, I therefore only have to look at 5 numbers rather than all odd numbers. So that's proof by exhaustion. So the final proof that we're going to look at is not actually a proof, it's a disproof. In other words, we're going to prove something is false by finding an example where the proof is not correct. So for example, if I wanted to know whether every person in England knows the smallest prime number, I don't need to ask every single person in England. So I just need to find someone who doesn't know the smallest prime number. And so it's quite often easier to disprove a statement rather than to prove it. And so this is what the final part of this presentation focuses on. It's disproof rather than proof. So if we can find just one example that's not true for a given statement, then we have found a disproof by counter-example. And these questions are often the easiest to do because we're just looking and finding a value that doesn't work, hence therefore disproving a statement. So let's have a look at an example of that. And again, by all means, write this down in your notebooks, please. So Ben says that for any natural number n factorial is always less than or equal to n squared. And we've got to prove that Ben is incorrect. So we're going to be looking to find one value of n where this doesn't work, and then we can stop because we've proven him to be wrong. But before we do that, let's just remind ourselves of a bit of notation. So natural numbers are our counting numbers starting from 1, so 1, 2, 3, 4, 5, etc. N squared is self-explanatory. N factorial, n with the exclamation mark. Now we've seen this notation when we were doing some work on binomial expansion, but just as a reminder, 4 factorial, as an example, 4 factorial would be 4 times 3 times 2 times 1, which is 24. 5 factorial would be 5 times 4 times 3 times 2 times 1, which is 120. So we are finding a value of n where this statement doesn't work. So the easiest thing to do is to start using a sequential, a logical system to make sure that we know where we're at with our working out. So I'm going to start with n equals 1, our first natural number. And if I put n is 1 into the statement, then 1 factorial, which is 1, ends up being less than or equal to 1 squared, which is also 1, and so that is true. So far, Ben is correct in what he is claiming. So we go to 2, and again, we're going to have a look at whether 2 factorial is less than or equal to 2 squared. So 2 times 1 ends up being 2, 2 squared is 4, and so we get 2 is less than or equal to 4, which is also true. So no problems there, Ben is still correct. We move on to 3, so 3 factorial would be 3 times 2 times 1, 3 squared would be 9, that works out that 6 is less than or equal to 9, also true. N is 4, 4 factorial is less than or equal to 4 squared, so 4 times 3 times 2 times 1 ends up being 24. 4 squared is 16. We've found an example where the statement isn't true. In actual fact, of course, 24 is not less than or equal to 16, so it's false, and therefore the statement is untrue for n equals 4. And so to conclude with our disproof, we would say that we have proved that Ben is incorrect as required. So there's an example of disproof by counterexample, finding one example where the rule does not work. And they're the 3 ideas that we would learn for year 1 proof. So it's your turn now. There are some questions on page 4 of the textbook, exercise 1.1. Have a go at those questions. Any problems, please speak to your classroom teacher, and then I will see you all on the next presentation. See you later.